Here comes August. How's it going, Augie? Direct your attention to the tasks for Unit 2, Lesson 3. That's what we're in today, the U2L3. You can find them on Canvas, either under assignments on the Science2 class page, or on the home page, scroll down to the weekly calendar to today's date. Today is 10/20/20, October 20th. You can see everything we're going to be doing there. As we've been doing, we'll start off with just throwing you into breakout rooms for a quick little share of the silly question. I'm going to throw the question in the chat right now. Here's your question. You have your own late night talk show. Who do you invite as your first guest? Which is an elaborate way of saying which celebrity or athlete or singer or whatever would you like to have a conversation with? You haven't answered this question before, right? This class hasn't done that one yet. Okay, I'm going to give you 20 minutes, 20 seconds to think about it, and throw you in breakout rooms to share. We'll come back together in 2 minutes. Breakout rooms are open. Share my screen to my iPad real quick here. All right, again, need verbal confirmation. Can everyone see a slide in front of them on Hewitt 5.7?
Yes.
Yes.
All righty. So centripetal force, as we've discussed, is counterintuitive. I don't know about you, but I used to always think centripetal force was this one, the velocity pointing forward, right? That it was constantly that tangential velocity idea. It is not. It is actually an attractive force pulling inwards towards the center. And so that's just something you got to memorize, right? Any force that does that would be considered centripetal force. It's always acting towards the center of spin. That's a good way to think about it. So I guess you could theoretically think about gravitational pull on the moon, right? The moon has tangential velocity moving around. So I guess that could be somewhat equated to tangential, or to centripetal force. Now, if we were to go into space, and this is something you see in movies all the time, there is a way to mimic gravity, and that's using centripetal force, right? If we could get a round spaceship that could rotate, if anyone's seen 2001: A Space Odyssey, or if anyone's a fan of The Expanse on Amazon Prime, they have these ships that spin and create artificial gravity purely through centripetal force, right? So the idea is that, and again, this is kind of confusing, but I like this image here where you see a person standing on the inside of a ring that is spinning. The centripetal force is essentially pulling the floor towards the center, right? That's the way to think about it. And so this person is just standing on the floor. And so they've got a force going upwards into their feet, which they're going to feel as weight. So that's what that force going downwards, that's their perception of weight. And it's created simply because they're inside this ring that is spinning around, and that force that is drawing upwards towards the center, that's from the floor. Think of it as the support force. That's the key thing, right? That's what you're feeling right now on the ground, or if you're sitting, that's the support force. And so we could artificially create that in space. And I don't think there's any actual spaceships that have done that yet. But what you were seeing in that jet in that video on the homework was mimicking that. Okay, projectiles are anything set into motion, right? By throwing it and then continuing in motion. And I'm going to try to keep this as simple as possible, just to introduce, and we'll add in some complications. But basically, you can split everything into the two forces, right? Horizontal and vertical, right? You've got, if you throw it, you've got one force pushing it parallel to the ground, and one force pulling it straight down to the ground. That's gravity, right? And since gravity is consistent, we can measure that pretty accurately. But the shape you get right there is called a parabola, right? That's that sort of bent shape. And if you were to throw the ball upwards, you would get this sort of, there's another example of a parabola that you would get. Acceleration due to gravity, it's actually not 10 meters per second. It's about 9.8 or so. I think it's 9.8 meters per second. But the point is that the ball, anything that you let go of on Earth that begins to fall, it's going to speed up by 10 meters per second for every second that it falls. So if it's been falling for 3 seconds, it's going to be moving at about 30 meters per second. Now, granted, air resistance complicates this a little bit, but don't worry about that. We're not going to go into that much detail. The point is that you can then adjust your angle of release to change the distance that's covered, but it doesn't change the amount of time it takes to fall, right? So that's always consistent. Assuming we're always releasing from here, then the gravitational force immediately starts to act on it. You do get more of a parabolic shape if you were to launch upwards at the start. And so that allows you to then change the distance, right, of where the ball strikes, if you were to throw it slightly upwards a little bit. And you can start predicting, if you're able to take these measurements, about where a projectile is going to land. And you'll be working with the simulation today to mimic that. The key thing to take away from this is what the homework emphasized, right, is that if you break it into horizontal and vertical forces, then it's kind of interesting what happens here. Again, we're going to assume that there is no air drag at all. So no drag, which is not realistic because you always have air, right? But if a projectile is launched from this point, then you can see the vertical force slowly reduces, right? It gets smaller and smaller until it comes to a stop, and then it speeds up again as it falls back down to the ground. But notice the horizontal never changes because there's no air for that to strike or slow it down. Now, in reality, horizontal would also slow down, but just for this little introductory part, we're going to keep it really simple and pretend that there is no air drag at all. Any questions on content from those two sections of chapter 5? I think it's pretty straightforward. All right. So again, I want to do a couple little activities to explore this. And the one you're going to do today is a flip grid activity where you're going to be mimicking gravity, very similar to how we saw in that jet flipping around. But you're going to do something a little bit simpler. It's called the water spin and bottle flip challenge. This is step number 5 on the tasks to complete list. If you click on that, it'll take you to the assignment, which has the usual instructions on what to do and what you'll need. You're essentially going to be filling a cup with about 3/4 full of water, getting into a clear space and doing a full spin around, right? Throwing it in a circle while holding onto it. And if you do it right, ideally the water will stay in the bottom of the cup. And you can reduce the amount of volume in your cup to about 1/4, and then you could do an even smaller spin and still keep it on the bottom. And then I'll challenge you to do 1 bottle flip as a result of that. But all the instructions are here. I have a little demonstration video I made as well. The same demonstration video is also on the Flipgrid page, along with all the instructions. So I will let you go to work on that. When you are done with that, so when you have posted your video, or at least recorded your video, remember to end by answering this question. There's always a question at the end of these videos. The question for this one is, how did none, or at least very little, of the water spill out when the container was upside down during the loop rotation? So if you're doing this right, you shouldn't be spilling any water. So the question is, why does that happen? Once you're done with that, there's an ED puzzle I would then like you to complete. It's the next step on the tasks to complete list. It's right underneath that. It's a bottle flip ED puzzle. It's literally 30 seconds long with 2 questions. But it goes into some of the physics about what's happening with bottle flipping, which is kind of that popular video trend for a little while. So I'll be here if you have any questions. I'm going to time for 20 minutes to get through this. But I'll keep an eye on the ED puzzle because, again, if you're done with the flip grid, you should move on to the ED puzzle that's there. And I can see who has that done, who doesn't. So 20 minutes, go for it. Let me know if you need help.